see you.
Robert, it's good to see you.
So Matt and I were talking yesterday, and we realized that we've been following each other on the Tech Talk for a while, and he sits there and talks to me during my Tech Talk, and I sit out there and talk to him during his Tech Talk. And we thought, let's just do it different, you know, because it's been the same video for 3 years now.
It makes me a lot more comfortable having everyone else up here too.
So we're just going to talk a little bit, but before I talk, I want to throw stuff at y'all because it's kind of one of the things I do. Let's see. I made a stack of these. These are commemorative shirt, not an official Shootout shirt at all.
Have the Shootout logo on
No,
there?
no, I did my own one. So, much like this from 11 years ago, just a little memento, just a souvenir. So I made a bunch of these. They're $20. I have them out there. Boom. All right. And then I made commemorative glow-in-the-dark wristbands too. Okay, let's see. Okay, I made koozies. I ought to give everybody a koozie. Woo!
Oh, this is flying.
Sticker packs. Don't get hit in the head with sticker packs and candy. There's candy in there. Got candy. Ooh, that was too close to you. I'm sorry. Yeah, you're a non-combatant. Okay, more stuff going. Woo! 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 That guy's getting a lot of
Losing an eye.
I made glow-in-the-dark cups.
Glowing tonight.
I made glow-in-the-dark sunglasses. They're not sunglasses because if they're glow-in-the-dark and you put the sunglasses on and then you couldn't see in the dark, right? So the UV 400 sunglasses are clear. Sweet. All right, so I just want to get everybody situated. Got more cups. I'm not going to throw them. I'm not going to hurt anybody. And I got what? That matches your water cup there. Okay, I got some more sunglasses and stuff. I'll just leave right there. Okay, so got that out of the way. So, turbochargers and stuff like that. I kind of was thinking that if I talked about safety, it might be a responsible thing to do. So, who has ever thought about turbocharger safety and how to be safer with turbochargers? Did it ever cross your mind? You know, it's something that a lot of people don't think enough about, I think. I remember a couple years ago, there was a video from World Cup Finals where a guy walks into his camper trailer and there's a hole in the wall and the mirror's knocked off the wall and the mirror's smashed on the bed and there's a turbine wheel sitting on the bed of his camper trailer. And he's parked on the other side of the stands from where the racetrack was. You know, and I think this past year.
Ejected the turbo out the side, about to drive his leg out. It was in the media. I remember seeing it. I can't remember where it was.
It happens more than anybody would like to admit, but yet we still have this tendency to want to build 2-foot-long aluminum downpipes for our cars. You know, and you know, in some cases you just need to not do that. You know, tractor pulling. I think there was a fatality recently. Tractor pulling. Yeah, tractor pulling has completely revamped their rules and required 3 cross bolts in the downpipe of the turbocharger. So in reaction to that death, you saw the sanctioning body basically take it upon themselves to do something. You know, I think it's a good idea to do something like that before somebody gets hurt. I've been talking about it for a long time. A lot of times if you get on the internet and you jump into a group where people are talking about building their aluminum downpipes and you say that's a bad idea, all of a sudden I turn into a safety first Clyde, right? And everybody's, wow, everybody, I don't have that weight on there, stainless steel, you know, but you know, that's a dangerous thing. You know? So you know, it's really something that I want to bring to the forefront more, and I want to keep talking about it, even though it's not popular with everybody. But you know, why do we stand right next to the cars when they're doing the burnout and the turbo pipe points right out the side of the car? You know, sometimes they come out of the fender. They point right at your face, and you're standing right there. You know, some people call it a downpipe. I like to call it a turbine cannon. Like a potato cannon, you wouldn't stick your face in front of a potato cannon, you know, even if it wasn't loaded, you know. So you know, that's something I'd like to talk about. But basically, I just kind of wanted to bring that up as a topic to talk about, and then just see what kind of questions you guys had. I think Matt had a few things he wanted to talk about too. So
Well, I think on your point there with the safety part of it, there's two sides to it, right? There's one side, the containment when you have the failure, and then there's the other side of it, how do you avoid the failure, right? So on the containment side, you mentioned cross bolts. Explain a little bit what that is, just for people that don't know.
So a cross bolt is a way to keep a turbine from going out with the gas. So, you know, how does a turbo work? It works off of, the first thing that happens is you build up a lot of turbine pressure to turn the turbine wheel with. But if the turbo breaks, all that turbine pressure becomes the motivating force for the turbine cannon. When the turbo breaks, that turbine's going to want to go with the gas that's going out the downpipe. So what do? In some classes, they have actually instituted a rule where the turbine housing itself has to have some bolts in it. Okay, and what they do is that at the exit, so if you were to look in the downpipe where you connect the downpipe to the turbo, you just see two great big 3/8 inch bolts going across the backside of the turbine housing. You connect your downpipe to that. But you don't have to wait for a turbocharger company to get forced into making a heavier housing that nobody wants to buy, okay? You can apply this to your own life just by taking your downpipe just past the turbocharger, drill a 3/8 hole straight through it, put a bolt through it, and put a nut on the other side of it. You've got a cross bolt, you know? So wouldn't it be easier to say, like, somebody gets, say you explode your turbocharger, you break your turbocharger by not avoiding it, okay? That's the second topic, right? Okay, but the first topic, say you didn't avoid it and it does happen, and the turbocharger explodes and the pieces are gonna come out the tailpipe, and somebody is standing there and they do get hurt. Don't you feel better if you say, you know, I was trying to be safe, and even though it's not required, I had a cross bolt in my downpipe, and that person would have got hurt a lot worse if I hadn't taken that step and been diligent about and conscientious of safety. So you could add these cross bolts to your own downpipe and achieve this level of safety very easily. Robert, I don't want to put things in my downpipe that hurt my turbine flow. It's going to wreck my turbine efficiency and cause me to not be able to spool my monster boost up to the moon and everything else like that. It's not true. It's not really what happens, you know. Turns out you can put a couple of 3/8 inch bolts in that downpipe and it doesn't really make any difference to the car. Now, if you're now, and to counteract that, in the Pro Mod 88 classes where they run two of these 88mm Pro Mods on a V8, we've tested bolts and not bolts, and you can go a mile an hour faster without the bolts, okay? But that's a really turbo limited case, okay? None of us are really that limited turbo wise that having a bolt in there is going to take a mile an hour off of your time. So it's a good thing to do. It's a prudent thing to do. It's a responsible thing to do, and I recommend doing it. Well, wow, Robert, you just, if I drill a hole through there and put a bolt, I'm going to have exhaust leaks. Well, you could take it a step further, right? You can weld on a little standoff on the outside of the pipe on each side. You can mill a little sexy little, you know, form-fitting button to go on there, take that on there, have it threaded on the other side, have a flat washer on this side. You can totally make it where it doesn't seal. Yeah, where it doesn't leak, or you could weld the bolt in. Okay, for example, I've seen that you want to change the bolt sometimes. Okay, because over time the bolt can start to melt and bend and, you know, degrade and stuff like that. Even if you use a grade 8 bolt, it can still have some corrosion and stuff like that happen to it over time, and it's going to be standing in the fire. So, you know, it's kind of something you might want the ability to change. You know, yes, you can weld it to keep it from leaking, but then you'd have to, you know, redo that when you need to replace it.
This applies to the bumper exit stuff.
Yes,
if it's under the car, it's going to follow it. As long as it's not an aluminum, it's going to follow the stainless.
Right.
Wherever it's going to
For the most part, it will. If you've got a normal, whatever gauge, you know, stainless downpipe, where do you normally make
16,
those at?
16
Yeah. So
gauge.
what's the wall thickness? So that's and that's not, unless there's a 90 right after the downpipe. that's going to probably keep the turbine wheel in there. It might poke some holes in it. It will poke some holes in it. Okay, it will tear it up, and it's like a meat blender thing. It's just terrible. It's a lot. There's a lot of energy in there. And the bigger the turbos are, the more energy.
Do something like an X ring, like an actual insert. It's an X with blades.
Yeah, I actually have a couple of designs for a couple of different discharge flanges that actually have like a Mercedes-Benz logo, 3 instead of 4,
yeah.
And put a little airfoil on them at a little bit of an angle. And I was wanted to make like a whole array of them at different angles, so you could change and experiment with them as an insert that will like go into the V-band clamp. And clamp right onto the outlet of it. I never got around to making that, but with this becoming more and more of an issue and more popular, it's popular of a problem. The problems get popular, but I don't know. This one seems to be popular.
There is actually something that we've done in the past that can improve performance and add this as a additional layer of protection. I learned about it from Alan Lockheed when I was telling him, we're running some 1980s Formula One technology turbos on my car. They're these old IHI turbos, and they have a really, really small discharge. So it's like a 2.5 inch pipe coming out there, which necks up to a 3 inch downpipe, and it's really small, and we got a lot of flow going through them. And what he was telling me, Alan's like, on the diesels, what they've been noticing is if they put basically a divider plate in there, which is just a straight thing that follows that 90 around, and they weld it in there, you get the protection of having that plate there in case anything happens. But the engine will see that as if you have a full 3 inch pipe on there, even though it's only 2.5. So it actually thinks there's a bigger pipe there because you've got this vortex, flow coming off this turbo, and it helps straighten it and get it out of the car faster, get it around the bend faster. So you might want to try experimenting with something that you might find something that you can do or something that can be incorporated that will add that safety dimension but actually improve performance too. So there's opportunities out there, or like the suggestion here and what you talk about your drawings on having something that might bolt in between the V-band clamp or something.
Yeah, integrate basically clamp flange system that has this insert in the middle of it.
Which could do that.
That'll be like the same material they use in car converters, like a titanium, so it makes
Well, you'd use turbine wheel material. You'd make an Inconel switch. You'd make it the same material to make the turbine wheel out of. That way, that's the best way to have strength at that temperature. Stainless steel doesn't have that kind of strength at that temperature. Or we make turbine heads out of stainless steel easier. But Inconel is what you need. When something's glowing red, but it still needs to have a high yield strength, you want to use a super alloy like a high nickel super alloy like Inconel.
So does that pretty much cover the containment aspect of it, or is there anything else?
Well, containment also, here's another containment problem that I see, and I'm really cautious about it, especially as you see the proliferation of Asian housings, Chinese housing. You'll see like, hey, you guys have really expensive stainless steel V-band housing, but we made a iron copy of it. Okay, so what's great about that? Okay, well, it costs $78 now instead of $300. So that's great about it.
But they didn't try to change the design.
But they didn't change the design to reflect the material change. Okay, so they copied the geometry of the nitronic superalloy stainless housing, so it's got a 6 millimeter thick wall, but now they made it in iron. Yeah. So what do you do there? There's no ductility to iron; it just punches a hole out of it. So beyond just ejecting out the downpipe, what happens when a flywheel explodes? Everything goes out in that plane of rotation. So containment, that's another aspect of containment you want to be concerned with. Is your housing thick? Is it appropriately thick, or is it a copy that shouldn't have been made? You want to be careful of that. And on S400 stuff, you see thin wall iron V-band housings, unfortunately, and I would recommend against using them if you can avoid using it. They are popular. They do save a lot of money. People want to use them. And on S400s, they run at a lot lower temperature than some of these smaller turbochargers that we're used to using. So there's an argument that you can get by with it, but you might not want to. I like how we always got the fast cars behind us and we talk.
Sound a little great.
Yeah. Yeah, here comes Nick.
Yeah, this
He's
is
gonna be fast.
this is the finish up from last night. There was oil down near the end of the night, so we moved this Q2 qualifier, which should have been done last night, to this morning, so that people wouldn't have to be here till 11 o'clock last night. So it's just a rerun of that. So
You ended up having 2 cars drive straight down the middle of the track doing oil the whole way last night, huh? That's
yeah,
a beautiful thing.
right before we were trying to finish
That's
up.
a beautiful thing, man. Yeah. So we putting their names on the website or what? The names of the offenders.
We should, right?
We should tar and feather it. Yeah, you should wall of shame.
Everybody signs a thing. If I oil down the track, I will pay $1,500.
Yeah. You can ridicule me on social media. I agree to it.
So, okay, so we talked about, so that's the containment thing. Make sure, just to recap, good quality stainless downpipe.
Yep.
You can use a good quality turbine housing, either a real cast iron one that's made out of, or made out of the right
Yeah, proper
thickness.
thick wall, like
Yeah.
normal thick wall. That's why cast iron housings are heavy. Is because they need to be to get the strength. So.
Or if you're gonna buy a tile or other aftermarket one,
Then
make
they're
sure
thinner
it's
wall, but
thinner wall,
but
make
they
sure
have the
it's
right
good stuff.
alloy. Yeah, from appropriate supplier. That you have faith in.
Gotcha. So we talked about that, or cross bolts, or something in the downpipe that's a mechanical way to stop that thing from traveling.
I know a guy that makes downpipes, and I'd like to hear his thoughts
Yeah.
on this.
So what do you think about this?
I think it's something that, especially for. when
Can
it
you
comes
see
to
yourself
the-
integrating
Yeah,
bolts
absolutely.
into this stuff
Getting
for
some
people?
ideas just sitting
I
there, absolutely.
think it's a great idea.
I can show you what was done to my downpipes with that little foil thing in there, and you can see if you could try testing it and see what you see.
Because, like, Robert's brought this up, and we never really even thought of it, that it doesn't come out straight out of the turbine wheel. It has that swirl.
Yeah.
Correct. So we're always trying to be conscious if you're going to reintroduce the wastegate flow, you want to do it so that it's merging like a highway entrance, not a 90-degree angle. So yes, you do have some swirl there, but that swirl angle changes depending on the load on the turbine. So when the turbine is in the spooling process, the swirl is one way, and when the turbo is at the wastegating level, then the swirl goes the other direction. It's crazy.
Yeah.
Yeah. So you're wastegating. That's when you want to match the direction of the flow. And that's why when I was going to talking about making those tri-leg inserts, I wanted to make them with different angles to the airfoil so that you could get it to cause the least problem for your application, but while being safety conscious at the same time.
And I don't know this for sure, but it seems like, so when you arrest that swirl and you get it to just go straight, instead of swirling and going around the entire wall and traveling that entire distance, if you arrest that swirl and then make it go straight out, even though it's a smaller downpipe, it makes it think that it's
the engine
larger.
responds and
I
turns
don't
like
know
it's
that
larger.
for sure, but it seems like that might be what's happening if you arrest that swirl.
Yeah.
Or before making the downpipe bend, if you can arrest the swirl. I don't know.
Well, you think about the catalytic converters go right on the back of a lot of new models, right? So, and what happens there? They're straightening that flow right there, So even when you get to be OEM level of engineering, where instead of having a guy make a part, you've got a company with $3 million worth of engineering staff. They're working on making a part. What do? They straighten that flow. They might not have a choice. It might not be their optimal choice, but they do straighten the flow, and they get all the performance metrics that they want to hit doing that. So
they do the converter now right on the back of the turbo. It's part of the exiting.
yeah,
housing.
you need to light up. You need to light the turbine. Yeah. You need to light the converter up really quick. So that's the reason you get it so close. But it also does that straightening function that you're talking about. I've never really investigated that part of it.
Yeah.
I've done a lot of thinking about the swirl and the different ways they swirl and the different twist rates to the swirl that can happen at different operating. Different modes operating. Sometimes it's a tight swirl, and sometimes it's a really long swirl. You think about gun barrels, like the twist of a gun barrel. A really tight twist versus a slow twist. Let's watch Nick for a second. Yeah, let's see Nick go. That is a fast car. I guess with Jason. Is that Jason Fletcher?
Yeah.
Did you go 67 yesterday or something?
Did he?
I forgot what he went.
It's hot here.
It is a little warm in here. Yeah, we prop that door open, probably help. Yeah, yes, stand by the programming. Yeah, we'll be right back in a second. We're at the racetrack after all. There we go. It's 16 and 1. Yeah, not bad.
So where has that swirl been observed? How do you know that it's going in one direction versus the other?
Have you ever looked at the inside of your downpipe? Because it's right there. It's right there. Yeah, you ever that spin art game thing you used to play when you were a kid? You got gray hair. You did spin art. Okay. Yeah. So what happens when you put a liquid on something and there's spin rotation involved? It's gonna go with the flow, so to speak. So you look at the inside of a downpipe, you can see traces of the moisture, the oil that's coming through, the engine, everything else. It's always a spiral pattern on the inside of the downpipe. You know, and that was just the first thing that ever made me start thinking about it. I was like, wow, yeah, that flow just doesn't come out. It comes out, you know, and you know, sometimes it's a tight swirl, sometimes it's a slow swirl. It just depends on what's going on. You put little kind of, you can put probes in there where you have a tube and you have a hole on one side of the tube. It's a cap tube. You put a hole on one side, and as you change the angle of that tube, when you maximize the pressure that tube picks up, that hole on that tube picks up, then you know you're pointing right at the direction of that flow. Basically, that's how you instrument that and observe it directly. Same thing like on a compressor cover. We started looking at the way that the air moves through the surge ports in the compressor covers. You know, and how do we do that? Well, you put a really sensitive pressure sensor on a tube, and you point it right at the port. Okay, and you measure. You know, is there lower pressure there than there is at the inlet? You know, well then that means that tells you which way the flow is going. Is there higher pressure there coming out of the port than was going in the inlet? It just tells you which way the flow is going through the port. You also put an open tip thermocouple, you know, right at that port. And when the temperature of the air of that thermocouple right at that port, the outlet side of that surge port, it gets warm, that's when you know it's recirculating and coming out. When that temperature gets cool, that's when you know the port changed modes and it's going into being an intake port instead of a recirculation port. So that's how you'd instrument that. That's how you'd know what it was doing and how it was doing it. By taking those kind of measurements.
It's kind of an oddball question, but I see a lot of guys in the DSMs bolting on housings and doing a wastegate as opposed to having it built into the turbo. But I don't. It helped me work this out because I'd rather have an internal gate instead of having it have to pass through, 2 inches of pipe to go to another gate using the same port on an internally gated turbo. Is there any difference in that, or is it in my head?
You've built a lot of O2 housings with tubes on them and a lot of wastegates on headers. What's your take on that? How long that wastegate tube is and what goes on with that?
I mean, you want to vent that pressure as quick as possible, and I think right there in the housing would be the way to do it.
So as far as like the height, it doesn't really care like if it's before or after the interface between the turbine housing or the manifold.
Okay.
So whether you mount the wastegate off the collector or off the turbine housing isn't going to make much of a difference, or if any. But the angle of entry into it is what's going to make the difference, and also the diameter of it and everything else.
So the distance between the turbine housing and the gate really doesn't matter too much.
Not as much as the entry into it, because the
And
exhaust
the
wants to keep going where it's going.
Right.
And if you make like something that can catch the exhaust and help it flow out the gate, that's going to make a much larger difference than
The distance between the turbo
exactly,
and
because everything's kind of collected and combined into one area. As long as you don't have like the wastegate like off one runner, as long as it's after the where the collector, where it opens up into one volume, it's not going to make a whole lot of difference. The placement's not. I think
I would agree with that totally. And I think part of your question that what was hiding in that question was you were talking about as it relates to DSM exhaust housings, kind of. Right. Okay. We didn't decide we wanted to do it that way. We had to do it that way.
Right.
Okay. Everybody, you couldn't just buy a T4 header for your DSM for $800, could you?
No, you can buy the HKS one for like 26.
Yeah. So we were stuck with the factory turbine housing. There's not one article on Project Talon that has
Nope.
a T4 header on it.
Nope.
Okay, that's what we had to work with. So we were stuck there. So when we wanted to have external wastegates, we just went with what we had to do. Functionality drove all of those decisions at the time. So you take the flapper out, you put a 1 1/4 inch drill bit in your mill, and you would drill that hole out, and then you would you'd lay back the short side, so that you had. Was that boosted?
That was Demon.
Oh, that was Wohler. Boosted won't run it out all the way down the track if it's not a wind. He wouldn't run a 9-1.
You won't do what?
He wouldn't run a 9-1. If it wasn't running past, he would stop and save it. He wouldn't run it all the way out.
That's smart.
So we really started putting the wastegates on the O2 housing in the late '90s because we just wanted to control it. Internal gates, there wasn't any more availability on optional internal gates than there was on headers. Okay, so it was just get you an HKS wastegate, make a flange, torch cut a flange for the side of the exhaust side of the turbo, take the flapper bits out of there, weld that stuff together, and put it together and get to the shootout. If you're holding the pressure in, you're holding the pressure in as far as the turbo is concerned.
Yeah. I think it's something important to mention too.
Woo! What was that? That was an RT car. That was Rafe, wasn't it?
Yeah, he was good about the 1,000 foot. I thought it was going to be a lot quicker.
What did I say? What did you say?
I was just going to mention, I thought it might be a good point to mention that the wastegate's just a hole in the manifold. So, and then like a larger wastegate is just a larger hole in the manifold because its whole point is to lower boost. So I think we hit this every year where if you want to run higher boost, you can run a smaller wastegate.
Yeah, you can run a smaller wastegate. Yeah. That's the question you get a lot, over the years. Is like, is this wastegate going to be big enough to run that much boost? And I'm like, just think about what you just said.
Backwards.
Write that down and think about it as you write the words down. If you want to run high boost, you can take the wastegate off and just block it. Okay, you run free float and just see what it'll do. Don't do that, yes, because then we'll go back to the first topic of containment, which we never came back to that prevention.
So
the
so
wastegate's
basically,
failing, just use my foot to get home, regulate.
Oh, yeah.
my
Yeah.
boost.
Yeah, you can do that. Yeah.
Throttle control is controlling boost. So,
You're not gonna run ET with throttle control, though.
no, just
But just transportation mode, yeah.
for conversation.
Get the broke car home thing for sure.
well, just one more thing before we get on to the avoidance part of it, avoiding the failure. Do you think, and this is a big misconception I think a lot of people have, what do you think happens to exhaust manifold pressure when the wastegate opens? Do you think the exhaust pressure goes down or the exhaust pressure goes up?
Probably goes up.
Why?
Doesn't change.
Because you're changing geometry in the turbocharger, and you're changing your exit pressures.
You got the right answer for the wrong reasons.
Awesome. Yes.
So what tends to happen is your exhaust manifold pressure when the wastegate opens will go up, which seems the opposite of what you would think. But what's happening is your shaft speed is slowing down, so now you're getting less flow through the turbine, and you're diverting flow through the wastegate, which ends up being more restrictive, so your pressure goes up.
Yeah, people want to talk about back pressure like it's a number. It's a curve. It's a function, and it's a function of a lot of variables at different points in the RPM. So, what was the EMAP? What was the EMAP at what RPM and boost pressure? Is really a better question. So, when I asked somebody to show me what the EMAP was, what I really wanted to show me is a screenshot of their data log with the entire power band there present, and boost present, and exhaust pressure present, so I can see what RPM it crosses over. to having higher turbine pressure than compressor pressure, because optimally you want that somewhere in the middle of the RPM band or towards the high part of the RPM band if you have a drag race car. If you have a road course car, you want that crossover point to be lower in the power band because you want more of the response in the mid-range.
Pressure helps build power too.
So, as far as the other topic, do you want to talk about that downpipe thing anymore? You should make some stuff like that.
Yeah, no, for sure.
yeah.
Variable geometry down by
Yeah, variable nozzle downpipe turbine catcher. Yeah. All made out of Inconel. It's only $6,800.
Okay, so now let's talk about prevention. How do we avoid the failure in the first place?
Well, you're going to monitor your shaft speed. Okay, you're going to monitor your exhaust back pressure. You're going to monitor your exhaust gas temperature. Okay, and how do you do that? Shaft speed is a difficult thing to monitor.
You just pull the front wheels up.
Did you really?
Yeah, cold pipe.
They're all over a cold dog. Yeah. So you want to monitor shaft speed, you want to monitor exhaust back pressure, you want to measure exhaust temperature.
Yeah.
Okay, here's that. This is gonna be a run. Let's watch this one. Against Richard Alm.
Thank you.
Wow. 712 at 202 for Devin. 802 at 180 for Rich Alm. So, that was nice pass. This is going to be great for the finals tomorrow, man. It's going to be real nice racing.
Yeah.
And I'm so glad the rain chances went away.
Yeah.
I got that too. I knew it. I wasn't worried about the rain. Never was worried about the rain.
Well, even if I talked to Bader earlier. He's like, for whatever reason, all my events have been raining out all season, but everybody else's events, like, they get like an hour worth of rain and we work around it. So I was like, he's like, you're gonna be fine. I'm like, okay.
Yeah.
So we were talking about containment. EGT sensor, that's pretty cheap.
Yeah, that's not expensive. And EGT sensors, you guys were, the Haltech guys were talking about sensors a lot. A trick I've started doing over the years with EGT sensors for two reasons is I put it in the downpipe now. Okay? I used to put it in the collector because I wanted to know what that max number actually was. But after measuring in the collector and measuring in the downpipe, 3 inches away from the turbine outlet, after measuring in both of those places for years and years and years, I started to realize you're 250 to 300 degrees Fahrenheit cooler at the downpipe than you are at the collector for most of the things that we do. Okay, so you could take that sensor out of the collector and not have a sensor that's living at that high of a temperature, so you don't have a lifespan shortage from high temperature. And then also, if you have the thermocouple fail and the tip come off of it, it doesn't go through the blender. Okay, so if you put the EGT probe in the downpipe just right past the turbocharger, it's a lot safer. It's a lot safer world for that sensor to live in. And you can just add 250 to 300 F to that downpipe temperature and have a pretty good guess of what the collector temperature was on the inside. So whenever you see temperature getting really high or exhaust back pressure getting high or really shaft speed getting really high, that's when you run the risk of shattering a turbocharger or snapping a shaft or something like that. Two-step events in the burnout area are some of the most stressful events for the turbocharger. You got a lot of throttle input going on. You got blow-off valves opening and closing. You got the engine doing machine gun. Its best imitation of an M60 machine gun on that turbine wheel. So if we're going to break something, we have a great chance of breaking it right there. That's one of the great places to break it. Middle or top top end of the track is where you break it otherwise, okay? As you really start to lean on it and put the load on it in gear, that's when you get a lot of shaft speed, and that's when you just scatter things. So you see shafts snap here at the front side of the track, and then you see things just explode from RPMs and from centrifugal force at the top end of the track. So you want to avoid those things that way. So how can I don't have any of those sensors, Robert. What can I do? I'm not hitting my boost target, and I just keep up arrowing on the wastegate duty cycle. Whoa! Don't do that. Don't do that. Every time it's not responding to your input where you're trying to tell it to raise boost and you're telling it to raise boost, you have a chance of telling that turbocharger, spin faster, spin faster, spin faster. I don't care that there's a leak. Okay? I don't care that I have a ruptured coupler. I don't care that I've split a seam on an intercooler. I just want you to spin faster because I don't want to do a boost check. I just want to explode the turbo and find out that way that I had a boost leak. So don't do that. Don't just keep up arrowing. Okay? If it's not responding to the input you're putting in, figure it out, man. So be conscientious that way. So shaft speed, temperature, and violent two-step events. Some people just don't like to run blow-off valves. You get this a lot in the V8 world. People are like, they're used to running S400s and GT55s and stuff like that. And you can kind of get away with it because the shaft on that turbocharger is bigger than my finger. But our smaller turbochargers, they don't have that luxury. They've got 1/4 millimeters, 6 millimeter shafts. Some of the smaller turbochargers you see on modern cars like B03s or BV50s on 997s, they might even have a 4.5 millimeter shaft. Okay, so these things get really noodly and they're really delicate. You got to take care of them. So how do you avoid not doing it? You don't just keep up arrowing. You monitor your speed, you monitor your back pressure, and if you're in a turbo class limited racing class, like say you're in 64.9 millimeter class, okay? Well, what is everybody doing? Everybody is running them to the moon, right? Well, how do you run them to the moon and not explode them? Well, you have to know you have to contact the manufacturer of the turbo and say, what speed should I not exceed for this turbocharger? And then you monitor speed and you run it short of that speed, so you avoid permanently deforming the compressor wheel and causing a failure of the turbocharger. You see these guys running these class model turbochargers, they are not just doing it out of luck. You see these guys in the 73.9 millimeter class. That's a big class, and I think some of the guys made passes here today are running pretty hot 73.9 millimeter turbochargers, moving more air than some 80 millimeter turbochargers can move. Okay, well, how are they doing that? With a lot of shaft speed. Well, how do you not break it? Well, how do you not break your engine? If the guy built your motor and the guy says you're good to 8,700 RPM and you go out and run it at 9,200 RPM and it breaks, what is your engine builder going to do? He's going to laugh his butt off, man. You're going to show him the data log of you spinning it to 9,200 when he told you to spin it to 8,700, and you're on 9,200 on a two-step, at a rev limiter or whatever, and he's going to laugh at you. I told you I was not going to do that. You can't do that. You wouldn't run an 8,700 RPM engine to 9,500. Well, you shouldn't run a turbocharger that's got 140,000 RPM limit to 170,000 RPM. The same kind of problem. So you need to understand what your limits are. Like Clint Eastwood said, man, always got to know his limits. You've got to know what the limits of that turbo are. You got to not break it. Okay? Like how do you run a small tire class? How do you run a small tire? You don't just cook the tire off of it. You got to know what the limit of that tire is, and you just got to edge that limit the whole way down the track. That's your responsibility as an operator. And that's why guys at Haltech over there, he's just humble over here is just shaking his head up and down. Exactly, measure. Know your stuff, know your data.
Yeah, get your data, because if you don't have data, you're just guessing.
I know. I'm getting guys coming all the time. Hey man, it won't do this, and I'm like, well, what is this doing? I don't know. I don't have that channel. Well, what about that? Oh, I don't have that channel either. I'm like, you just want me to guess? I'll just guess. I'm gonna preface my whole advice with this is a guess, though.
Right.
Whereas if you gave me information, then I could say. Physics would say, based on what you just told me, that this is what's happening.
Right.
Then I could be really confident in my answer. But if we don't have any information, then I can guess for you. I got a pretty good crystal ball, to be honest with you. I've been looking at it for a long time, and I'm kind of right sometimes. So I still give you some good advice.
Guys, when everything explodes the turbo, before when we're overspinning Adriana's turbo and it doesn't make any more power, and I've been there in all these situations.
Yeah.
100%.
Do not just keep up arrowing, actually down arrow. If you turned it up and it made 7 pounds, like 7 less horsepower, you should have down arrowed instead of up arrowed. You should have walked away from that edge. It's not trying to hang 10 off the end of like Gidget at the beach. You got to back up a little bit and ride that surfboard. It's going to work better.
When we were talking about this, because you have a thing, and we talked about with the racing and stuff, class limit turbos and the whole problem that it creates, which is why we're talking about this subject now, basically, because that's what brought it to the forefront. But one of the things that we talked about, and I was saying, well, what about other, different compressor materials? What about a titanium compressor wheel or this or that? And what you had said that I thought was more applicable than anything exotic like that was thinking about how that strength of the compressor wheel changes with temperature.
Exactly. Yes.
That is a big thing that people overlook. They go out, they make a pass. Well, let me go make another pass right away. Their compressor wheel's not starting out at 100 degrees. It's starting out now at 300
degrees.
Yeah, 350 degrees.
And it's going to get hotter during that pull.
Yeah.
And it's going to get hotter during the next pull. So if you just,
do you remember some of those numbers? Because it was pretty dramatic what happens, I think, over 400.
You get to around 350 degrees Fahrenheit with a 2600 series aluminum, and you have about 50% of the strength that you had at room temperature. Okay, so you think, you look at the material and you go, oh wow, that's really strong material, and then you do analysis on your part and you go, oh my god, we could run it to 350,000 RPM, okay, and not exceed the yield strength on that part. Well, look at there's no red spots on the FEA. It's great, okay, but that's great if you put in the room temperature strength of that material. If you put in an operating temperature for that material, the yield strength that corresponds to that, you'll see that that's much lower. It's much lower. So you see that with aluminum, you see that with every material. I don't even know of a material that gets stronger as it gets hotter. Just about everything I can think of is going to have a reduction in yield strength as temperature goes up. I don't even know if there's any. Yeah, you got one?
No, I just have a question.
Oh, okay. So I was like, chill out. Lay it on. Yeah. McKinsey, right?
Yeah. I just had a question that it may sound a little bit out there, but if it's the temperature of the compressor wheel that you want to keep under control, what about if you put a nitrous nozzle in front of it that allow you to run more shaft speed? I know it's a quick change in temperature, and you're probably going to lose some of that power.
Okay, here's what I know about that. Okay, I have seen, and I think it was Volvo that did this testing. Okay, that I read about. And if you want to see some people that really spent money to answer questions like this, you're going to find white papers that are in the SAE library. Okay, but I want to say it's a Volvo document that I read that talks about this. But how quickly does the compressor wheel change? This is actually an article about turbine wheel temperature, but it relates the same way. I'm talking about the air going through affecting the blade itself. Like how quickly can that air transfer heat to that blade? Not as quickly as you think it can. Okay, so on the compressor side, that inlet condition, that'll help. You spray some methanol or some water in the front of the turbocharger, it can help, but that's never really going to touch the wheel exactly, okay? So not as much as you'd want it to, probably, okay? What happens is that wheel temperature just kind of does this. As you make a pass, you make another pass, you make another pass, you just need a delta T event, and you don't have a delta T event when you're spraying that fluid into the inlet, even if it's vaporizing and you get the latent heat and everything from that. There's not a whole lot of time. It's not present there. It's not present there. And that's the same reason why you can get away with crazy EGTs for drag racing sometimes if you want to, because we started near ambient, right? And the turbine head, it was maybe 400 degrees Fahrenheit, until I do my burnout. Then it's maybe 500 degrees Fahrenheit. By the end of the go down the track, it's glowing red. Okay, so when is the yield strength of it going to be small and low enough for you to scatter the turbine wheel? At the top of the track, again, like I'm talking about, you're going to snap shafts and stuff at the front part of the track, and you're going to explode things in a centrifugal way near the middle or the top of the track. So you see ballistic blankets and scatter shields and stuff like that. We have to have scatter shields for transmissions. We might have to think about scatter shields for turbos. You saw Precision adopt like a Kevlar blanket around some of their turbochargers that they knew were going to get pushed really, really hard, just to prevent having problems. Like I said earlier, if you do end up having your car hurt somebody that's standing there, when you get on the stand and that guy is asking you questions about why you were so reckless with your behavior and stuff like that, you get to say, I wasn't as reckless as you are thinking, sir, because I took this method, and this method. I employed these things to try to improve my safety, even though I was not required to by any sanctioning body. Just upon myself, I took it upon myself to add a blanket, to add the crossbows, to add a scatter shield, because I'm conscientious. And yes, I am trying to be as safe about this as I can be. You want to be that guy. You don't want to be the guy that's like, yeah, whatever. Yeah, aluminum down point, putting my front left caliper. You know, what happens when that 90 millimeter turbo wheel shoots through that aluminum downpipe that's pointing right at your front left caliper, man? How are you going to go down? You're going to 150 mile an hour in the middle of the track or the top of the track. You don't drive with one headlight, sure. One tire, one front tire, no. You got the other one who just went wonky. Okay, you know, so it's worse than having only one driving tire. You got one driving tire and you got one that's departed from normal behavior. Yeah. Aluminum downpipes just light me off, dude. I knew I was going to get all excited talking about aluminum downpipes, man.
We don't make any.
Yeah, well, yeah, good. Yeah, I wouldn't expect you to, but you know, you get into the VA world and they all want to run these aluminum downpipes. And I don't get it. I don't understand it. It's not safe. It's not a good idea at all. Not a good idea at all.
One of the weakest metals, and you want to have the most pressure.
Yeah. We were already talking about strength and temperature. Like, what am I use aluminum for? You know, people go, oh, it's an aircraft alloy. Aircraft are cold.
Yeah, they are.
Those are cold, man. It's freezing up there. Yeah, you lean your cheek against the. If you could touch the outer skin of that airplane with your face, it would freeze your face off. You know. So, you had a question
I
about
think it's just the price difference between aluminum and titanium, because they're about the same weight. So
Yeah.
money's
Yeah, you know, I don't think I'd like titanium for containing anything either. Titanium can end up being kind of brittle and breaky and snappy, and I like a gummy stainless steel material for it. To be honest with you.
Titanium breaks and shatters.
Yeah.
Usually go really thin because they can too.
And then on top of it, there's a tendency like, well, hey, if I'm going to spend money on titanium because I want it to be light, I'm going to get the thinnest titanium I can get.
It's like all you can get, kind of.
Yeah,
1 millimeter thick.
or half millimeter. You know, that's paper.
Does
Yeah.
the grade of stainless make a huge difference though?
Not a huge difference, no.
Not for that.
No, not for a downpipe. I wouldn't think so.
Well, I mean,
Yeah.
like, you use stainless for your bolts going across.
Oh, I would probably on the bolt material. I'd probably defer to what's been going on so far, and like the SFI, I think cert for the Pro Mod class is it's a grade 8 3/8 bolt. Yeah, just it's a plated grade 8 high strength steel grade 8 bolt, and they make it where you can change them. You know, because like I said, that's an environment where you're going to get some degradation of that bolt over time for sure. You know, and you want to take it out before it looks like a big
Woodpecker
curve.
got to it.
Yeah, because you're not gonna be able to get it out very easy if you wait until it just melts into a curve. You know, so you want to change those every once in a while. Would be my opinion. But like the tractor rule was way different than NHRA rule came out. The NHRA said they wanted the 2 bolts right at the exit of the turbo wheel, and they want them right next to each other on the turbine housing. And then the tractor sanctioning bodies, they want 3 bolts, and they want them in the downpipe at a certain distance from the turbo, and they want 1 bolt, and then change 30 degrees, another bolt, and then change the other 30 degrees, and a 3rd bolt. So you have like 3 bolts spaced 2 inches apart. You know, and to me that seems like a great way to bleed off that energy. You know, it's rather have one event where you have the 2 bolts there. You might be able to smack them, you know, and snap them both at the same time. You rather have stagger them, and so you kind of make a net, you know, to catch that with. You know.
It's a 1500 degree cannonball.
Yeah, you don't want to mess around with it. You know, there's a bunch of videos out there, but one of my favorite ones is this guy's dynoing a diesel truck, like on a dyno that's at the edge of a building, and it shoots, and diesel trucks like the stacks that do that. So he goes, "Ka-pow!" And there's like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, comes down, bang, and it looks like dreidel. It's just like spinning like a top on the ground, you know. It's like it's sizzling, you know. It's just steam and smoke coming off it. But it took like 3 or 4 seconds for it to hit the ground, man. You know, that thing must have gone 100 yards in the air. You know, it's still spinning. You know, I don't know, 20,000 RPM, but it hit the ground. You know, you're gonna grab that with your hands. You're gonna have a hand. You know, just nasty stuff.
Flying over things.
Yeah.
Plane goes down. All that.
Yeah. we should do more about it. We really should. It's our responsibility to do more about it. And, you know, I'm trying to by just educating and talking about it, making it be something that's normal. You know, it's a really good idea. I mean, you know, do you ever feel attacked as a drag racer? Just like people don't want you to do this. People don't want you to mod your car. People don't want you to live your life and have your fun. They're just trying to steal your joy and stuff like that. I mean, I feel that way all the time.
California, so yes.
You know all about that. Okay? So, you know, if we're responsible and we take actions ourselves to be responsible, then we can last longer on the playground before mom comes out there and snatches us up by our ear. You know? So,
Perception that what goes on is not truly what goes on.
well, you know, in Texas, they just passed a law about street racing, and they're talking about intersection takeovers. So they just passed a law in Texas where they can seize all these cars now for street racing. I'm like, guys, that's not street racing. Street racing happened about an hour and a half out of town on the highway at the Beltway over there, and you guys didn't even know it was happening. These are not street racing. You guys are not street racing. These guys are criminals.
Yeah.
I mean, I guess if I'm street racing, I'm a criminal too. But you know, I'm trying to go and not bother anybody. The intersection takeover people, the purpose is to bother people. The point of that is to bother people. You know, so yeah, it's a terrible visual. You know, it doesn't help us at all. So I think I saw some shirts, a program the other day, like Hot Rodders Against Takeovers or something like that T-shirt. You know, it should be a movement, man.
Yeah.
You know, if you know people that are takeover people, you should punch them right in the face.
Did you see the one in Pontiac? There was a guy who stole a car out of like Toledo, came up to Pontiac, Michigan, was doing the takeover in the intersection, and then there were some street racers that were street racing, and all three of them got taken out. Like just bad timing of stupid people street racing.
Hey, you know, that's why it's important to support tracks. Okay, if we don't keep tracks open, you know, and then we're screwed. We really are. Okay, so say your local track has an event, you're not planning to go. Go buy a damn ticket anyway. You know what I mean?
Yeah.
Go to their website, buy a damn ticket anyway. It costs $25. Wow. You know, wow. Don't go to Chili's. Buy a ticket. Buy a ticket to the event you're not going to anyway. You know, I sponsor little events at 8 Mile tracks around my area all the damn time. Hey, here's $300. Here's $500. Put my sticker on your flyers. Put me on your T-shirt. Here's $500. You know, they're like, wow, thanks. I'm like, I like you being a track. I like the fact that you're a track. I like the fact that you have events. You know, I don't want you to not be there. You know, and I can't fund your track or anything, but I could support you.
Yeah.
You know, I could try to be behind what you're doing. You know.
I mean, in Southern California, all we have is an 8th mile track. We have Irwindale. I mean, it's the armpit of drag racing. It's like the worst track ever.
There's so many
But
great
that's all we
tracks in
have.
Southern California,
That's
man.
all we have. But so, you know, that's what we do. We go out there, we support it, you know.
Mhm.
We tell people to go there because it's great if you're a shop owner to get your customers out there running their cars, trying to reach a number, trying to get quicker and faster. That's why they're going to spend money. You know, it's great if you're an enthusiast because you have a safe environment to go do it.
Yeah, I was gonna say there's an ambulance right here.
Yeah.
You know, and that guy can keep you alive till a helicopter comes, and then there's a hospital not very far away, and all it's gonna happen, boom, 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 boom. Okay. Now it seems like forever when your car's on fire for the dude to run over there with the fire extinguisher, but really it's 14 seconds. It's all it took him. It didn't take forever. It took 14 seconds. It's pretty fast, you know. So you can bitch about the track taking a long time and why did they do this and that, but all you're ever gonna do is bitch about a track. And I'm just trying to say we gotta stop. We gotta stop bitching about tracks, and we gotta support tracks. It's not an easy thing to do. Yeah, it's not an easy thing to do. And every time I hear somebody bitching about Mike Ferrara, I was like, that's not an easy job.
Yeah.
Okay. Okay. You go try to do that job and make everybody happy at the same damn time. You're not going to do any better than that guy does. Okay. So just deal with it.
Appreciate
You
it.
know. You go do the job and see. Okay.
Well, but you know, I gotta say, this year of all the years, I think I don't know. I really kind of felt a change in the community, kind of supporting the event and stuff. And you know, it's been a big deal on us, you know, because the cost to rent this facility went through the roof.
Yes.
You know,
yes.
and it's like
it was never a cheap facility.
It was never
right?
cheap, but then
Yeah.
when COVID and everything else, and you know, I mean, in California right now, I can't hire people at my machine shop because why would I want to go work for you when I can just go to McDonald's and make the same or more money?
Yeah.
You know,
yeah,
you're
it's
probably having the
crazy.
same
Yeah,
problem.
it's crazy.
It's insane,
Yeah.
but I don't know. I feel like the community's really starting to gel better.
I'll tell you,
together.
one of the things that impressed me was this kind of grassroots effort to raise prize money this year. You know, and there's a reason. There's a reason that Red Demon is here. There's a reason that these really fast cars are here today, and it's not because we were going to all clap for them and give them a trophy. It's because they want that money. They want that prize money, you know. So you go ahead and take personal initiatives to help tracks make events work better. You know, that's allowable. You know, that's allowable. You know, reach out to promoters that are working on events and say, hey, I'd like to work with you. I'd like to try to help support what you're doing. I had this idea. You know, can I help? You know, I want to do this. You know, you get just support. You know, just be a friend. You know, just be a friend to tracks. Be a friend of promoters. You know, and you know, always wear your seatbelt. Suntan lotion, you know, sunglasses, all good ideas. You know.
Eat your vegetables.
Eat your beans, eat your greens, man. Eat your greens. Yes, sir.
You guys do a lot of custom stuff. If we sketch out, measure, design, and send you prints, can we clone it and copy it, or do you like to have the stuff right there?
We really like to have the stuff right there, just so we can account for everything. But what we've definitely done in the past is, for example, let's take like a forward-facing DSM setup. It's not as easy and as modular as an Evo where you can go with like a half radiator and everything goes out great. So like on a DSM, if you do a forward-facing setup, a lot of people want to have the compressor go straight into the intercooler air intake, right, for the air to air. Well, you have the frame rails there, so you can't do it. You can do it like straight up front and then have like a water to air because it's really short and all that. But if you want to do an air to air, you have to have a tube front end. Well, all the two front ends are different. So
A lot of variability there.
Oh yeah. So we have you know, get the two front end done, and then you place the turbo where you want it, exactly for your setup, for your intercooler, wherever you have that mounted, whatever the turbo is, everything. And then you make something between the cylinder head flange, exhaust flange, to the turbine housing flange, connect them pretty rigid so that when you ship them to us, nothing moves around.
Sure.
Describe that something a little bit more. Okay, like what do you want that to look like? Do you want like a head flange?
Yep, like
and then a turbine inlet flange.
Yep.
And then you want like a 2-inch box steel tube connecting the two flanges so that
something rigid
yes,
that's not
okay.
going to move.
Yeah.
Because I mean, if we're going to make a manifold, a lot of time goes into it. And
Yeah.
if you
Oh, sure.
take the what we request too is like really think everything out where, like exactly where you want it, and then because we're going to make it exactly where you put it. Or I mean, what we might do too is if you have a turbo, we can like clock things a little bit,
Sure.
but know that it still keeps the center line of the turbo exactly the same. But we might clock the collector angled up or down or whichever. But yeah, that's what we can do is build it exactly off of that so it fits your exact setup. And that's a setup where every setup's gonna be a little bit different, but you do that to plan everything out, and then we make a manifold that places it exactly where you would put it. And for example, on Nick's memorial car, Jesse, I don't know how to pronounce the last name, Abel, I'm gonna say.
Yep.
That's exactly what they did. They placed the turbo exactly into the inner. It's not quite a forward facing, and it's not quite like a top mount, but they placed it exactly where they wanted it. They sent us a fixture. We made the manifold. You know, they sent a bunch of photos and everything too to make sure that we're not gonna hit anything else around there, just to get an idea of what the constraints are. We made it, sent it. It worked out. Like, super happy with it. And it's down there and doing cool stuff. So.
I hear a lot about manifold design and flow characteristics based on cylinders and location. You take that into consideration when doing. I mean, I've seen pictures of V10s with crazy freaking balloon manifolds. I'm like, what the hell is this? This is so dope.
So there are a lot of design considerations, and we've done some testing for different. I really want to get into the runner size thing because there's some fantastic, like really interesting stuff that I've been like chomping at the bit to bring up, and if you don't mind sharing a little bit, but the runner size, I'll just say real quick, most of the time the runner size that's used that looks natural based off the port size and everything is typically too large. Up to a certain power level, like you typically want to use the next size down, which we call the smaller runner. It doesn't look quite as impressive most of the time, but as far as like the actual like driver's seat, like it actually makes like a noticeable difference. Power per PSI and response, like you don't have to choose, like it does for certain applications, like it really does everything. It's just fantastic. The length, we definitely look at the length depending on the setup. I mean, there's a lot.
So watching these high ride guys dyno out these heavy headers, and they end up taking hammers to them and pounding them half their size and not making a single bit of difference.
I love that video. I've seen
And
that
in
one
my
too.
mind,
Yeah.
in my mind, it just tells me it's too big of a header anyway. You know, you want to trap that heat so it gets out as fast as possible, not have it expanding in the exhaust pipe.
Yeah, less internal volume for the manifold for the exhaust pulse to dilate into, but more so what ends up happening is not the entire exhaust stroke isn't created. There are certain really important parts of the exhaust stroke. If you're looking at just one cylinder, when it first fires, or when the exhaust valve first opens, it's not as important, but when it's just about to close is what determines how much exhaust gas is remaining in the cylinder itself. And any exhaust gas that's remaining in the cylinder effectively makes the engine act smaller, because there's less intake air charge that can then fill the cylinder.
You'll get guys in that situation where they're not emptying exhaust really well. That it's very easy for them to make boost, and you'll see these guys like brag about how I can run 65 pounds of boost, or I can run 55 pounds of boost. Here you look at their setup, you're like, well, I know why you can do that. You know?
Yeah.
Because you got 20 pounds of pressure left over in that cylinder when that exhaust closed. It was very easy to fill that cylinder. It was very easy to charge that intake manifold because you had all this residual gas left over. I bet you're running about 4 degrees of ignition timing too, right? Oh yeah, how'd you know? You know?
On some setups, it's not as much of a bragging point that you're like holding like 40, like it depends on the setup, but if you're like bragging that you're holding 40 PSI on a fairly small turbo, it doesn't really equate to like a bragging point.
You're actually showing your hand because you're showing that you're trying to push it too hard. Because you should have just let it run a speed line. You look at a compressor map, speed lines kind of do this. You just want to put it on that high speed line and go, oh, it's going to make 24, and it's going to make 26, and it's going to make 22, and it's going to make 20, and it's going to make 18. Okay, and that's the best performance you could get out of that turbo is right on that high speed line. Anything more than that's going to explode it. Anything less than that's not going to be using everything that the small turbo had to offer. Okay, you got a big intercooler, you're going to cover up any efficiency problems. You want to run it at the max speed that's not going to break at. Get all that air, even if it's crappy air, get all of it, run it through your awesome air liquid intercooler, make it cool again, and you're good to go. Yeah, but, a lot of people don't think about residual gas being left over like that and what that does to boost, but that's a real thing.
Yeah, and then too, more efficient setups will take less boost to do the same thing. So when you're talking about maxing out the turbo, a more efficient setup will take less boost to.
Yeah. The V went up, the boost went down, and the mass flow went up at the same time. Like sometimes I'm a little happy when somebody calls me with the problem of I put the new turbocharger on, but like now I before I even got to the same boost I was running at before, I'm having to add all this fuel. What's going on? What's the matter here? You know, I don't even have it cranked up yet. And I said, but the system VE went up. Okay, you're moving this air, and it's easier for you now. Don't be upset about that. Don't be upset about the fact that what you used to do at 38 psi is now happening at 33 psi. That's what you were aiming at. But I want to run 38 psi. It's just a number. It's just a number, man. It doesn't matter what that boost pressure is. We're trying to make power, not boost.
Boost is the amount of push.
We're not going to post our boost curves on the wall. We're going to post our power curves on the wall. We're going to post our time slip on the wall. We're not going to compare EMAP graphs. You know what I mean?
I'd say the best comparison I have is amperage, voltage, and resistance.
Yes, they're related, but you can't just trade one for the other. You know,
this is the voltage, and the air actually coming through is the amperage.
Yeah, mass flow rate's like amperage. Yeah.
But what ends up happening is that higher boost is because you have that much more residual exhaust gas in the cylinder.
That's not healthy.
Yeah, it's the
No, you can't use your ignition timing then. You can't do what the engine's capable of doing. You know?
Yeah, we'll see on, we do a lot of RV engines and we get some customers, I just want to run the low lift cams and stuff like that. I'm not going to do any head work and stuff. They'll take the same turbo and it'll have to run about 26, 27 pounds of boost that we can make the same power, same turbo at 19 pounds boost when the head's ported, when they got the right cams in,
and that's
everything
less
else.
thermal load on the exhaust ports. It's less thermal load for the exhaust guide. It's just less of everything for the motor to deal with. So longevity goes up when boost pressure comes down. Yeah.
Yeah.
I guess I can kind of attest to speaking on some of the runner sides.
Come on up.
Sorry.
No, that's okay. I'll sit off to the side. So I
McKinsey Lange, everybody.
Yes. Yeah.
Black one G.
Yeah, I've got Black 1G. It's got stock wheels on it. So just a little rundown. These guys have been nice enough to lend me a couple manifolds to do some testing. Small runner versus large runner. And just to give you kind of a little rundown of my setup, it's a 2-liter aluminum rod, 10.5 to 1, dog box car with a 9569 with a 64 housing V-band, and then that's pretty straightforward. I've been doing a lot of testing just on boost, just to see what kind of differences we've had. Because after I started getting into doing the Zona stuff with Robert, I started diving a little deeper, seeing if we could make it more efficient. Because just like these guys were talking about the efficiency before, I put his turbo on, and now all of a sudden I'm making way more power with 8 pounds less boost. So as far as the runner situation, I started out with the small runner, their standard mount small runner V-band manifold, and I put that on my car. And just for reference, the car this weekend, I got one pass, a test pass on it. It spun, it traps 160, it weighs 3350 with me in it. So it's probably somewhere around 952 kilos, which is very respectable for that turbo. So at that level,
Nice for 16mm turbo.
I mean, there's, you can do some more with it. If I wake it up, it'll be fast, but
Just being modest.
it's honestly just getting the data was important. So with the small runner, I didn't do any small runner testing here this weekend, but I took it out and did some testing with it, and I found that the VE increase in the lower end was substantial compared to the large runner, to the point where it almost made me second guess at this point if the large runner was right for my situation, because I tried a couple different tests just to see, and with monitoring shaft speed on that turbo, typically if you follow the line, it's got 117 RPM limit for a constant duty cycle.
Yes, steady state use.
Steady state use, correct. And what I ended up doing is I ran it just a tad beyond at 124K, but very steady. So the car made probably somewhere around 850 or 900. But what I found was that the large runner manifold didn't start showing improvements until 8,000 RPM and up on that setup. And monitoring drive pressure as well, they were very similar. And actually, the small runner tend to have a slightly bit less. Now, I'm monitoring it from the EGR port on the manifold, which, talking with Kevin Jewell, that might be some discrepancy in that in and of itself, but it was something that was interesting to me as well. And being a stick car, I wanted to see down low just to see how well the car drove. And the car's been on a very similar setup for many years, other than switching the turbo. But this year, when I started with the small runner, just driving it around it had significant, it needed a lot more fuel. So,
Which means it's working better.
Which means it's working much better, and it compounds up. So anywhere in my low load to medium load areas, I would see 8 to 12% more fuel throughout. And just to show what that kind of does compounding itself, is if I took my car out, I did that on the same day, trying to get it very similar, same stretch of road, because I'm really close to a lot of stuff, and I'd like to do more testing with it at higher levels. But if I stab the throttle at 3,000 RPM in third gear, same spot, same time, everything else the same, just swapping that manifold, that small runner manifold came into boost 3/4 of a second sooner than the large runner did. And so overlaying that graph, you could really see that. And then if you overlay the power band itself, you saw that it was very similar, and the large runner didn't start outflowing the small runner until over 8,000 RPM. Coincidentally enough, at that same time, the drive pressure just peaked 1-to-1. So anything after that, it started cresting that 1-to-1, but everywhere else, it was less than 1-to-1 drive to boost pressure, which was really interesting to me because as a street car driver, I like the transient response. I like having that VE down low, and I like that if I miss something or I bog it, it's going to be able to pick up and make that transition really quickly. And it showed it to the point where I'm on a Haltech Elite 2500, and I do a lot of the data acquisition and tuning stuff myself just to see. And in that time, when I first put the small runner on, I actually had some misfiring because it couldn't compensate quickly enough in the lower RPM because of how much fuel it actually needed. So I actually had to redo the bottom end of the VE map just to get it close enough that it would drive. But the difference in feel in the car made me question everything that I had originally thought, honestly.
Right.
Because I'm like, man, this thing feels like an HX35 car or something. It's coming up so well, but yet it still makes the power, and that's where I'd love to do more testing, and I was hoping to do some more testing today, but I just shattered my transfer case, so that's kind of the end of that. But there will be more to come, and that was kind of my findings so far. So.
No, that's great information.
Like the whole point to begin with, because like you were pretty set on like the large runner, right?
Yes, I was like
To begin
point
with.
where I coated it, I put EGTs on it, and I'm like, this is definitely
See,
good.
that's nice. I love that. You show up and you've got like, I know this is what's going to work, and I'll show everybody. I'm going to put that one on the wheel.
Well, now at this point,
You know, and
I'm
you learn.
almost determined.
Yeah.
I'm like, I need to put more into this to see where this wall is, because it doesn't hit a wall. It doesn't seem like, you know, your air pressure doesn't shoot through the roof at a certain point. It just slowly tapers off. So it's not like it's a bad choice once you get to that level. It's just might not be ideal. Let's say if you're doing runs like this. So
Tracking
it's
160.
Yeah, I mean, and a full weight car. Yeah, these guys could be. I mean,
It's kind of been like a period. I mean, so we did testing a couple years ago, and we kind of it went up to, it was like a 700 wheel horsepower setup, and then small runner performed it everywhere, which is super cool, even peak power numbers. But we knew that, you know, above that, eventually the large runner is going to be the better choice for sure. It's going to have that crossover point. We reached out to Mackenzie because we're like, this car is going to find that crossover point. It's a 95 pound, it's 9569S. It can flow a
Got
ton.
enough
like-
turbo to show you
Yeah.
how the header's going to
Yeah,
work with it.
exactly.
Yeah,
You can
yeah,
actually
yeah.
find
Yeah.
that wall, find
Yeah,
where
the other test that you did, the turbo was small.
It was a 62 millimeter versus 67.
Yeah, so you got a small turbo. You're trying to see like how can header changes affect the power? Well, the turbo maxed out in both
Yeah,
cases,
exactly.
so it's hard to see the difference
The
in
turbo
the
was the
header.
limit.
Yeah, so you need to do a test again when the turbo's not a limit. Yeah.
So like the whole point of this was like, let's find the wall. But what's been really astounding is even on a, let's just 850, 900 wheel horsepower setup.
at 870, the car would trap 152. So that's dyno jet numbers. Right now it traps
See,
160.
you're in the upper 10 percentile of project cars at that point. So that's considered a fast car. This is as fast as they get almost, you know. So,
And I like
and you're even thinking, wow, small runner's the way to go.
Yeah, at this point,
Yeah.
and that's where if it comes down to it, and people ask, I've been saying honestly, the small runner has been, it's substantial. I mean, the difference is substantial, and it actually kind of translated over to the hot sides with the tile housings as well, because I did a lot of testing with different hot sides on that, and
People don't want to run the smaller hot sets
It
either.
doesn't make
It doesn't make
sense.
sense. But then you try it and you go, I like it.
yeah,
You know,
it's-
one-to-one.
And people all the time will tell you, like the tile, like the GT42 collector on the tile housing for the GT42 go, why is that 2 1/4, man? That needs to be 3 inches. I'm like, it does not need to be 3 inches. It does not need to be 3 inches. It
Yeah.
works better like this. It don't work better like but the headers I got just got this huge V-band on it. And I said, well, just put another cone on it and bring it down to this. Yeah, this is what you need. You want to work better. You wanna work
One of
better.
the things you can do for your testing, since you do have access to a dyno jet, is you know, what you see as far as trap speed, yeah, that's ultimate horsepower and stuff, but if you really just want to build a car to go as quick as you can, look at the amount of time it takes. I like to look at what my RPM drop is between first and second gear, so I know that's what my power band needs to be. You know, if I'm starting at 5,500 in second gear and I'm shifting at 9,000, that's the band that I care about. So do your testing where you're seeing what's happening when you take the amount of time it takes to get from 5,500 to 9,000 and compare it with the two manifolds. And if you find that you're
0.2 seconds quicker, you know, whatever it is, on the small manifold, you're going to go quicker down the track with a small manifold. So
It was actually very similar because my power band itself, I take my car out to typically 9250 or 9500, and when I shift, it comes around just under 7,000.
Okay.
So depending on the gear situation, but that
See,
turbo,
that's a regime you would normally consider you would want a larger header in. You know,
Yeah.
1,000 wheel horsepower, 7,000 and 9,000 RPM. You do put checks in all the boxes that say big runner.
yeah, and
You know,
somehow it
but
just
no,
doesn't.
no.
But the fact that the turbo, it lights up quick. So I mean, the difference between that and my old turbo, the 9569 would come into boost and be full, it'd be up to shaft speed, up to power by $6 grand or less was substantial. And that's in third gear, of course, but it was a pretty big difference. And to have that extra 1,000 RPM, that if, you know, I early shift, if I blog it, to have that little extra, where some of these guys with the large turbos, they don't have that kind of leisure where it's
done,
like,
yeah.
if they get under that, it's done. Where
Yeah.
the car bogs, they're done.
If they
That's
pedal
it.
it, it's over.
Yeah, if you pedal, it's over. I don't have that consistency. I'm not that quick like those guys. So it's nice to have that kind of, just that little bit of an extra, you know, that leeway. So if something comes down, I can bring it right back up
Yeah.
right away now.
Nice.
It'd be interesting to see too, another parameter you might want to look at, if your shift time is pretty consistent, see how much, if any, boost you have as a drop on your shifts. And if the amount of boost
So,
you're dropping on
I
shifts.
did. It was actually very similar.
Oh, it was very similar, okay.
I just implemented a strain gauge this year. It's still an H pattern shifter from that we make with the DSM 3D creation stuff where we just rebuilt it. So there's really nothing fancy, like there's no lockouts, there's nothing like that, but it's got the strain gauge put into it, so it's 90 millisecond second to third and 75 third to fourth, and it's very consistent. And with both manifolds, I saw the same amount of drop and the same amount, it would come up. The transition for the small runner actually came up a little sooner, but if you look at the boost curve itself over the RPM, you would never know until you actually overlaid the graphs and saw the VE and where it made the difference, which was incredible to me, because if you looked at it and you're like, oh, I put the small runner, it should spool like 500 RPM sooner. I saw 80 RPM difference, which is minimal.
Yeah.
When you think about it.
Well, it's almost experimental error.
Yeah,
Really.
and it could be at that point with how close it is.
Yes.
But that's kind of the difference too, is if the VE has increased, then at that same boost, it's making more airflow, and it's essentially acting like a larger engine. So even if you were to, and hopefully this is going to happen, where you can get it on a dyno and do a back-to-back test, even though I know it's a huge hassle. But you might, what we've seen before in the past in back-to-back testing where it does change the VE, the boost curves will look really similar, but when you overlay the dyno graphs with the horsepower and torque curves, one is shifted over. Even though the boost curves are really similar, if that higher VE is there, it's more
it's gonna make power
and it's
there.
realistically, it is actually coming on sooner, even though the boost curve doesn't necessarily
Yes.
show it, because it's making more power per PSI of boost during that. And I guess I want to be really clear that like we're not, it sounds super biased against all the large runner stuff.
It does.
But the whole point is like pushing to see how far you can go with the small runner, because a lot of people are like, I don't really want to go with the small runner because like
I'm
once
gonna
I
grow later. Yeah.
go above like we just stay safe and say like usually 750 and above to go larger. But it's just been so interesting that on like a, let's just say 900 wheel horsepower setup, the small runner is like hanging in there. Like
Yeah, that makes sense, because you really look at that header like it's an investment. It's not, it's not a cheap thing. It's not an easy thing to make. It's something you want to buy and use for a long time. And the two manifolds that you guys are talking about the testing data on, that's a normal production part for you?
Yeah.
So that's like a normal part number that you have on your website then? So I wanted one of those manifolds, like say I'm watching this video right now and I was like, I want to buy one of the damn things he's talking about right there. If I went over to your website right now, I could find these manifolds we're talking about. So what's kind of your lead time currently, like today?
18 weeks. That's the best it's been for several years.
Yeah. So you just get go order one right now, and in a couple of months, few months, you'll be able to have a header. Nice.
What are the diameters of small and large?
I think I must have right now. It's basically 1.25" pipe size and 1.5" pipe size, which means nothing for the actual size. But I'd say for a comparison, it's about like 1 5/8 tube versus 1 7/8 tube, or like somewhere around there. So like the larger runners, the more typical looking and looks more like typical.
That 1/4 inch makes that much of a difference.
It's more than I'm trying to think. I think it is about 1/4 inch.
I'm just.
Yeah.
It makes a lot because it's an area,
Right.
So
And it's
you
off.
change the diameter, but just there's R squared thing out in there.
Quarter-inch
You know?
tabs
It's a big,
type pie
it's a big
type
difference.
What's
And
the
like
actual pipe you run?
Schedule 10 because we use 321, so we can. It's usually overkill to keep schedule 10.
Another thing that I've been trying to wrap my head around is intercooler size versus lag and temp difference.
I can't speak to that.
No, me
Yeah.
too.
Like, one more time.
Intercooler
That was
size.
kind of loud.
Sorry, I know. Intercooler size versus intake air temps and boost lag. You know,
There's,
I
there's,
gotta-
you don't have enough room in the front of your car to put a big enough intercooler to have boost lag based on the intercooler. So the easy thing with intercoolers is the same easy thing with exhaust systems, as big as you can fit. What I'm talking about. That's the answer to that.
Yeah, here's that
Testing on that. I went from so a 2.5 inch setup.
Yeah.
It was very similar. It was on a 64, 66, 52 pounds, a lot of back pressure. But besides that, the car was making, it was around 800, 850 at the time. And I switched from the 2.5 with a 4-inch ETS, 2.5 all the way up to my same intake manifold. And I switched to a 3-inch, to an ETS 6-inch, to a 3-inch all the way up. And I thought for sure it'd be like my exhaust. I picked up 40 horse by going from a 3-inch to a 3.5
Right.
exhaust. And I thought for sure this would make a huge difference as far as lag and power. And obviously, the lag test to the power because I don't have strict data on the lag portion. It was very minimal to the point where just that 6-inch was 80 RPM, 100 RPM, which, I mean, you're filling a substantial
Substantial amount of room, yeah.
So it's really not.
Let's do a little simple comparison though, real quick, okay? So say you had the intercooler and it has a volume, okay? Let's say we double that volume, okay?
Yeah.
Now let's compare that volume or the doubled volume to the volume of air that's going through the car. One's from the ground to here, and one's from the ground to here. They're orders of magnitude difference from each other. The total volume of air that you're sending through the motor versus the percent change of volume you made to that intercooler is nothing. It doesn't matter. You go, oh yeah, but I put a 3-inch pipe on there. I made it 6-inch thick instead of 3-inch thick. I doubled the volume of that intercooler. That's going to take a lot longer to fill. Buddy, I'm filling your engine so fast that it's backing up and making boost pressure. Okay, so I'm delivering way more volume of air than the increase you made with your pipe change to 3-inch or doubling from a 3-inch intercooler to a 6-inch intercooler. That's insignificant. How many cubic feet is that? Okay, small number of cubic feet, different. Okay, well, we're moving 1,000 or 1,500 cubic feet per minute. So the change that you made in that is really insignificant. I always look for metrics like that. I want to compare two things that I think are the same, but maybe they're not. Are they really the same, or are they really off? And that's one where they're really off.
The reason I ask, I have a 2.5-inch core right now, and I have a CTS or ETS 4-inch core, and I'm trying to see if I throw that 4-inch core if I'm going to have a later RPM.
No, you're going to make better power. You're going to go from having a 3 or 4 psi pressure drop trying to get that air to go through the small intercooler to having a 1 psi pressure drop of having to go through the bigger intercooler.
Gotcha.
So you just made life easier for the turbo. You're going to run 2 psi less boost to make the same power now. Okay, by putting the bigger intercooler on it, and the lag's irrelevant.
Yeah, when we were at about 900 horsepower on the RV, we went from about a 2.5-inch to a 4-inch. No, I'm sorry, 5-inch thick core, and we picked up I think 87 horsepower. Same boost level.
It's easier to push the air through it.
Yeah.
In your comparison, what was the difference in intake air temp when you went to the bigger core and the bigger pipes?
For me, so typically with mine, I've got a full front bumper, so I've only got that small little difference down there. So the depth made a difference. What I was trying to do in just a strict in a quarter mile, trying to reach back to that. I don't for a third gear. Let's say for a third gear pull, I would see a 15-degree difference with the 4-inch, and then with the 6-inch, it was 8. So it was substantial, but keep in mind too, my car is missing half of the front mount as far as
the cooling area.
the cooling factor itself.
I think
so.
a bigger factor on intercoolers is the design of the core. You've got your bar and plate versus your tube and fin. I'm a big proponent. I like the way the Japanese do it. Tube and fin is really the way to go. It doesn't have as much mass to it, so a bar and plate works a lot like a heat sink. And the bigger it is, the more it's just, you have to heat it up and it pulls out the heat that way. Where
without airflow.
Yeah, without airflow. Where a tube and fin is really using airflow to extract the heat out of it. Right. So I'm a big tube and fin proponent. That's the way. You see the Japanese manufacturers of intercoolers, they'll always use a tube and fin. They won't use the brick.
The brick stuff foils through it. Yeah, it's very similar.
But for drag racing, the brick works pretty good, especially if you have a limited amount of space. Because you've got this giant thing that's just going to be a heat sink that's sucking up all this heat out of it. So it works in that. But if you got a street car you want to drive around and stuff like that, tube and fin is definitely the way to go.
And touch base on that a little bit, the quality of the core. Just switching from a low quality core to a high quality core, I saw a difference in about 20 degrees.
Yeah.
Not to mention pressure drop.
Yeah.
Right.
Yeah, well, a lot of times people will call me and ask me what they think they're asking a turbo question. You know, why is my turbo not making this kind of power at this boost pressure? And I'll get them to measure, relocate your boost gauge over to the inlet side of the intercore and tell me what the boost is now. And they're like, why don't I set 14 psi higher on the inlet side? Because your intercore is a problem. This has a lot to do with why you're not making the power. This go back to your question that you asked me to begin with. Why am I running? Why am I not making this power? I should be making this power. My friend has the same turbo, and he runs his at 38 psi. And he makes all this power. I'm running mine at 38 psi, and I'm not making that power. Well, if you have a 10 psi drop across that intercore, you're not running at 38. You're running at 48 pounds of boost as far as the turbo is concerned, and that's the work it has to do. So that's the work that's present in the exhaust side of the motor. So that's going to limit power production. So they're directly related. Intercore pressure drop gets overlooked by so many people.
And even suction side before the turbo.
Yes,
that's very overlooked.
Yeah. Well, you'll run it out on the 997 guys, right around 800 horsepower. They want bigger turbo, and then they get to one point and you go, hey, well, I want to go to the next size, and I'm like, you can't have it. Why can't I have it? So many turbos. And I'm like, you can't have it because it's not going to make any more air with the 997 intake system. You got a box on the back of it. There's very limited room. Going past 800 horsepower is really hard to get the air to the turbo. The only way you could go bigger is just not even have an air inlet system. Just put a cone filter right on the turbocharger. But then you're inhaling dirt air from under the car. So you got to pick your poison there. Inlet conditions has a lot to do with it. You go to the top of Pikes Peak. Inlet conditions have a lot to do with it. We do turbos for a lot of different guys that go up the mountain, and I love doing it because you learn stuff every time you help another guy with a project. About the way the engines react to going up the mountain, and the way that the way you have to manage the turbos. And sometimes you use turbos on hill climb cars just to keep the starting line horsepower level, just so the guy has a consistent power level going up. So you might run 4 pounds of boost at the bottom of the mountain, but you might be running 10 pounds of boost or 15 pounds of boost by the time you get to the top of the mountain, just to keep the power stable.
At those elevations, you're using the turbo anyway to compensate for the lack of barometric pressure.
Specifically, yes.
Yeah.
Any questions?
Okay, go ahead. Like transient response, like what I've seen in my own car is it's very temperature dependent. Like if I pull to the line and I try to spool the turbos up with no heat in the motor, no nothing, it struggles. But if I got it been idling for 10-15 minutes, get up there, I can right on the transfer.
Well, that might have more to do with the transmission than anything else, because the physics of that would be that if the intercooler is cool soaked and everything's cold soaked, and the under hood temperature is cooler, not been sitting there in the lanes with the AC idling for 10 minutes, that air would be denser, and you should be able to spool it better. So that might be a situation where you got conflicting things going on at the same time, as far as
testing it. Yeah, transient versus
The only thing I've seen that maybe supports yours, I have seen once in a while when we get a car and it's not warmed up at all. It seems like maybe that the turbine housing is maybe pulling some of the heat out, you know, to warm it back up to kind of, because there's a bigger delta T between what the exhaust gas temperature is and what that turbine housing is. So maybe you're seeing a little bit of that, but you know, the viscosity of the transmission oil and everything else changing with it, that is also affected.
I think that the viscosity of the transmission getting up on the stall and everything's gonna make a big difference too. But to kind of relate it to more to like where we're coming from, and what you were saying about the turbine housing, there can be a lot of heat. If nothing's like the turbine housing's cold, the manifold's cold, you have quite a bit of mass to heat up. A lot of that energy is going into heating that up versus the energy from the turbine.
So, which is not a compressor characteristic. Okay, we're not talking about the ambience of the compressor and whether it's inhaling dense air or thin air. You know, if it gets to inhale dense air, it's going to do everything faster. If it's inhaling thin air, it's going to do everything slower. But at the same time, you know, if you are having to get temperature into all the exhaust there, then that's energy that's not going into the airflow. Exactly. Turbine takes 3 kinds of work out of the 3 times the energy out of the turbine flow. It takes temperature. The temperature is less from the inlet to the outlet. Okay, it takes sound waves out. When that exhaust valve opens, pop, you make a pressure wave. That pressure wave is a piece of energy. It takes that out. That pop is muffled by the turbocharger. You get less of that pop coming through. And then thermal sound wave energy, and then the last one is the conservation of momentum, just how much mass flow is going through there. So just think windmill. Yeah, I mean, just think water well. Yeah, so there's no velocity going on. There's no impacts or anything there. It's just conservation of momentum and converting potential energy into a rotational speed on the thing. So that's just a mass mass flow transfer of energy, momentum based transfer of energy. Those are the 3 ways you get to do it. So while you're heating your whole exhaust system up, you don't have any of that. You don't have that temperature getting to the turbine wheel, so that it can take that part out. That would be a trend that would explain your observation in there. So if you have a lot of heat in the exhaust versus not having a lot of heat.
That's something we actually have to account for during the back-to-back testing to make sure that one's not stone cold, because you will literally see it in the back of
Yeah. You gotta take a temp gun and just shoot the turbine housing and make sure they're kind of close before you get started.
Well, as the temperature goes down, the pressure's going to go down. You know, you got which law was it?
Ideal gas law.
Oh, ideal gas law, that's right. So they're always going to go hand in hand, so you're going to have less drive pressure.
Good questions today, guys. Yeah. I'm about talked out. I need to throw some lost.
Oh wait, we had a question back here.
Yes, sir.
I was just going to ask about the turbine size, like the housing size. Is that dependent on the wheel design?
Yes. Okay. Like for example, with zone rotor UHF turbines with the splitters, you typically will run a smaller AR with a turbine wheel that's that style. And that lets you take advantage of what the turbine wheel can do for you and maximize on the spool rate that you get out of that turbine wheel that has a lower inertia because of the design of it. Compound that low inertia characteristic with the smaller turbine housing characteristic, you get 2 things going towards faster spool, and then you put the turbine wheel in there with the UHF turbine design, and then that adds your top end flow rate back into it. So that lets you capture that wider operating range. That's like cake that you get to eat instead of just looking at cake. That's it. You get to run a smaller turbine housing with UHF and still maintain the same flow rate and back pressure level that you would have had with a larger turbine housing and a lazier responding turbo if you had a standard turbine wheel.
Perfect example being Mackenzie's car that's just above 1-to-1 on the point. Is it the 0.64?
Yep, it's a 64 housing, and even switching from like a 64-66 with an 82 AR. So that turbo, I mean, we're talking 4 mil bigger compressor wheel and much larger. What's it?
64 millimeter, or sorry, 69 millimeter versus a 66.
Yeah, so a much bigger turbo in general, and just getting that, you'd think it'd come on a lot slower, but it would have better drive pressure ratios at the end. But what I found just doing the testing was it actually came on 300 RPM, 250 RPM sooner than the 64-66, and out the back, the drive pressure was substantially lower. So like on the
despite having a smaller turbine housing on it, still lower drive pressure.
Yeah, and I thought for sure it would be something I would be fighting a lot.
It's always a hard sell when I'm trying to explain that or to convince somebody. And I think I remember talking to you about it last year. You're like, that doesn't make sense.
It doesn't.
You know, and I'm like, you should try it though. I'd really like you to try it.
And after trying it, my biggest concern now is just making sure the shaft speed is under control. And that's where it goes back to what you guys were talking about before. It's extremely easy to overspin that turbo. So I've got a 4-port and my base wastegate is 36 pounds. And I've got 25% duty cycle in it right now to run 50 pounds. 1% duty cycle raises that 2 to 3 pounds. So if this gets any bit out of control, it's super easy for that turbo to now just spin and take it from there. And it's going to feed itself, and that's where it just it's a vicious cycle where if you can't keep that under control. I think that's going to be the bigger, not problem, but the bigger thing to keep an eye out on with these smaller
It's a loaded
housings
gun.
than anything.
It's a loaded gun. You can hurt yourself.
And you don't
with it.
know if you're not monitoring shaft speed. You're like, this thing just keeps making power and power.
Yeah.
My drive pressure isn't increasing like you typically would find on something that's you know a standard.
It's a different animal.
It is a different animal. That's what it's been surprising for me every step of the way, to be honest with you. But
I mean, I was gonna say too, maybe that like some people go with like the 1.03 on a 2 liter. And I think those are made a little bit more for larger displacement engines.
Oh yes.
Because like the 2
You gotta realize sometimes we put a 69S turn wheel on a 8-liter Viper. 103. You know, like 2,000 horsepower on an 8-liter Viper. You put a 105 69S with a 103 turbine.
But then you only need what? How much boost to do that?
You run like 25 pounds of boost.
Yeah. But when it's like a 2 liter, you're already running that much more boost. You already inherently, the turbo needs that much more drive pressure.
Yes.
So everything in the exhaust side is already condensed down anyway.
Yeah, because you're trying to get all that air to go through 4 intake ports instead of 10 intake ports. So it's a totally different game.
And then everything in the turbine housing, everything is a much higher pressure ratio just baked in.
Period.
So everything's already that much more condensed in the turbine housing, so you don't need the huge housing to...
No, you're not trying to get that. You're not trying to get the flow through at a low pressure. You're trying to get the flow through at a high pressure ratio, at a high drive pressure. So that fits with the turbine housing just fine. Well, I don't think everybody. Anybody else have anything else? Anything else you want to add to that? I'm about talked out.
Thank you.
Okay. All right, cool.
thank you guys.
Well, thanks everybody. Appreciate y'all coming and listening.
I just want to say quick that Mackenzie does a lot of the tuning himself, and he offers that service, and he also owns DSM 3D Creations, and I just want to throw that in there too.
And he's a smart guy to talk to. Yeah, get questions looking for somebody can help you with stuff. Mackenzie's a good resource.
Thank you. I'm getting the free lemon. I run flows across the edge.
We'll go to Q&A. We'll wrap it up.
This is a deal.
Hey, thank you.